All right, and welcome back. This is an introduction to basic first-order ODE solvers for Physics 2500 Intermediate Mechanics at the University of Windsor. So I'm also uploading these slides so that you can follow along. What we're going to talk about today is how to plot your data and how to solve these differential equations. So as an example, you already know how to solve this. I think this is one of the first things we did at the beginning of the semester, was calculate the trajectory of a ball that you throw by a person at some angle relative to the ground with some initial velocity. So you have some person, they throw a ball at some angle theta relative to the ground, some initial velocity v naught, and horizontal direction is x, vertical direction is y. So the first order ODE, the first order ordinary differential equation to solve, is that our Vx is V naught cosine theta, of course, and Vy is this V naught sine theta minus GT. And we can integrate this once to get the analytic solution that x of t is V naught cosine theta plus x naught. So whatever this x position is, often we call it 0, but you can call it whatever you want. And y of t is V naught sine theta minus 1/2 GT squared plus y naught, and we can call y naught this height, its initial height h. All right, and so what we want to do is go over how to plot this. The position of the ball is a function of x and a function of y, or x is a function of t and y is a function of t, and then discuss how to turn this into a parametric plot. So we can plot it as a function of y as a function of x. So we'll go to our spider code that I've uploaded. So this is on first order ODE. As you can see, I wrote this last year for intermediate mechanics class, and this is an introduction to solving first order ODEs. So I've commented this a lot. I've arguably over-commented it for those of you who know how to program, but for those of you who have never programmed before or don't know much about it or the syntax, I've made a lot of comments so you know how to work with this. Again, we start with this importing matplotlib.pyplot as PLT, as we did in the first tutorial. And we can also import the NumPy library, the numerical Python library, as MP. And something I didn't mention last time is something also that I like to do at the beginning of my code is plt.close and then bracket with a quotation mark, single quotation mark, all, end quotation mark, and parentheses. This closes all of your previous figures that might have popped up from the run. As I said, I like having my figures pop up in a separate window, but then if you keep on doing this over and over again as you're debugging your code or changing some parameter, you'll end up with dozens of these plots, and then you won't know which one is the one that you want to look at. So if you do plt.close all, that'll actually close all the previous runs. I also like importing time and then have some way of knowing how long a program runs. So I do import time and then have like timer start equals time.time and then with open and close brackets. So it doesn't require an argument, but it tells you the absolute computer time since, I don't know, January 1st, 1970, something like that, down to the nanosecond. So I like doing that because then you can tell what time is at the end of the code versus the beginning, and then you can see how long this code takes to run, in case if your code is really inefficient or something like that. When you want to create new sections, you can use this, the hashtag or the numerical sign, and then percentage sign, and that will break this into different sections. And so the reason for that is if you hit Shift and Enter at the same time, it will just run that block. So if I go up here, so it'll just run this block of code, which is nice. And then you hit Shift and Enter at the same time again, and it just goes down. And so that way you don't have to run the entire code all at once. So what we have is, in this first example, of this person throwing a ball and this ball, going through this trajectory, all we want to do is plot out what we already know from our analytic solution. So as I say, in this first example, we're throwing a ball relative to the ground with initial velocity v0. This initial velocity will be given in kilometers per hour, so 108 kilometers per hour with an initial angle at 45 degrees. So if we're going from kilometers per hour to SI units, then we have to convert. So our V0 will be this V0 in kilometers per hour times 1,000 to get to meters per second divided by 3,600 seconds in 1 hour. And also, although we might be more familiar with angles in degrees, often we'll actually want to work with angles in radians, and so we'll have to convert from degrees to radians, and so we do that by taking the angle in degrees, multiplying by pi, and then dividing by 180. And as I said, pi isn't an inbuilt number in Python, and so you need to have you need to import it through the NumPy library, and then so it's np.pi, and that gives you that value to, I can't remember how many decimal places, 18 decimal places or something like that. We'll specify that height, this initial y0, is 0, and gravity is 9.81 meters per second squared. And then nt will define as our number of time steps, and so it has to be an integer number. So if, for those of you who aren't familiar with it, if you put in something like, so this is easy to see, we'll call this AA is equal to 5, and I hit enter, you can see what pops up here is AA is an integer with a value of 5. But if I call AA equals 5.0, now AA comes up as a float with a value of 5.0. In the lin space, so it's a linear space array, which is through the NumPy package. This nt, this number of points here, has to be an integer. The starting point does not need to be an integer. The end point does not need to be an integer. But this last point, the number of points needs to be an integer. And so if you define AA as 1e1, we can see it's defined as a float value of 10. But if you define AA as int 1e1, then it's actually an integer value of 10. So instead of 10.0, it's 10. And so Python will be okay with this. Then we set up our initial velocity in the x direction, and so that is v0 np cosine theta, and our velocity in the y direction, which is np sine theta. And then we already know what the answer is because we've already been able to do this second order differential integration in our heads, and so we say that x of t is this v0 x times t, and y of t is v0 y times t minus 1/2 gt squared plus this initial height h, where we specify that h is 0. So we create our new figures by saying plt.figure with no argument, and then we'll be plotting this x of t as a function of t here, and we'll be labeling this plot, this arc, this trajectory, with x-coordinate, and then the y-coordinate will be labeling it as y-coordinate. And then we can also label our x-axis and we can label our y-axis, just so that we know what units we're in and things like that. And then we, in order to actually call these labels, we have to put in plt.legend, and that allows us to call those labels. And then just to finish it off, we put in a title. All right, so let's run that. And that looks like this. So the x-coordinate increases linearly with time, as we expect, because x of t is just v0 x times t, whereas y actually has this parabolic trajectory that it starts increasing and then ends up decreasing. And we can see this is labeled x-coordinate, y-coordinate. And you can change that to whatever you'd like. However, although that plots the position as a function of time and the distance as a function of time, typically if you're standing next to somebody and they're throwing a ball, you don't see the ball as a function of time, you see the ball as a function of position. And so that's what this next plot is doing here, is we create a new figure and we plot x of t versus y of t. So xt will be the horizontal variable and yt will be the vertical variable. And we then label the x variable, y variable, and title it as well. And we run this with hitting shift and enter, and that runs just that one block. And we can now see that the height of the ball as a distance that we threw it, follows this trajectory as we expect, this parabolic trajectory. And this is called a parametric plot because t is now a parameter. It's not a variable, but it's parameterized. Okay. So for that, I will finish off this one just talking about plotting these solutions, and then the next video will go on to Euler integration.